Hello, my name is Vikram and my registration number is 18BEC0967 and my slot is A1. The paper that I've selected is an efficient floating point multiplier design for high-speed applications using Karatsuba algorithm and Urdhva-Tiryakbhyam algorithm. So the first question asks us to explain how the selected paper is related to the COA syllabus. So as we've been taught before in the course, the adders, subtractors, multipliers, most significant and least significant bits, shifting and bitwise operations for 8050 and microcontroller. So here we are doing similar operations but for a different architecture and a different algorithm. The algorithm that is being used here is the Vedic algorithm, which is also known as the Karatsuba algorithm. So the floating point format that we've used here is shown in this block diagram, which I have simulated in draw.io over here. So in order to show that I've made this myself, I can move around the blocks like this, and I can select the entire thing and I can increase or decrease the thickness as well. So what I've done here essentially is that I select a shape from over here, then I drag it on to the respective places and I can type in whatever is required, like sign calculation. Then in order to direct the arrows, I simply hover over the box and direct it towards whatever is required, like this. Then the binary multiplier used is the Karatsuba or the multiplier model, which also I have simulated in raw.io, which is shown here. Again, I can move around the blocks like this. I can select the entire thing and I can increase the thickness like this. Yeah. So also what the similarities between what is being taught in our course and what is being done here is the sign calculations and the addition of exponents, just that the algorithm that we've been taught was the Booth's algorithm, but here the algorithm used is different. So moving on to the next question, we have to draw the existing architectures that are discussed in the paper. So the first architecture is the Harvard architecture for the Urdhva Tiryakbhyam multiplier, so which I have simulated in raw.io as well. So I can decrease the thickness for the entire thing like this. So I can move around the blocks like this, and then what I've done here is I've chosen a shape, for example this rectangle, then I place it over here and I can type in whatever is required, like adder 6, and similarly I choose a cone, then I reduce the shape, place it over here, then I hover over it simply and I can direct it towards like this. And to change the arrow, I can do this, I can do this, I can do this like this. So the other models that have been used here have also been specified in the previous answer. So here we have the Karatsuba Urdhva model, which I already showed in the last answer, and the floating point multiplier as well, which I've shown over here, and the Karatsuba multiplier. So the next question asks us to tabulate the performance analysis. So the first table, and all of the tables have been tabulated in Microsoft Word, and for the Karatsuba Urdhva multiplier we can see that there is a slight increase in the slices, LUTs and IOBs and delays as the bit size increases for the multipliers. Similarly, for single precision the difference becomes quite large depending on whether it is single precision or double precision. Then we have the delay comparison for various 8-bit multipliers. So for our multiplier we can see that the delay is very less, which means that our system is more efficient. And similarly for 16-bit, again we can see that the difference here is even large between what was there between the 8-bit multipliers. Then for the 24-bit multiplier, the difference increases even further as compared to the 16-bit multiplier. And similarly for 32-bit, so as the bit size keeps increasing, the delay keeps decreasing. But the difference keeps increasing between the different bit sizes. So the fourth question again asks us to simulate the architecture. So I've already simulated these here, which I've shown in the previous answers. Right. So here the algorithm that we've used is shown here. So what is being done is it's being divided into 7 steps for a and what is being done is in the first step we multiply the A0 and B0, where A0 is the least significant bit for the first number and B0 for the second number. So first we multiply these two. Then in the next step we simultaneously multiply B0 with A1 and A1 with and A0 with B1 and add them. Similarly, we multiply B0 with A2 and B2 with A0 and A1 with B1, and we keep on doing that, and we keep on shifting towards the right for the A element and towards the left for the B element, and finally we add all of them to get the final result. The transistor level internal diagram is shown here, and the simulation is being done in Verilog, which is shown here. Yeah, so the proposed architecture with the existing architectures which has been taught to us can be compared in a way that the UT multiplier, the A1+TA1 multiplier architecture uses Vedic mathematics compared to the one that we've learned which uses the Booth's algorithm, and the ancient system of mathematics which has a unique technique for fast mental calculations based on 16 sutras. So our algorithm basically uses Vedic maths to calculate and operate upon the values that are being chosen by us. So this approach is completely different from other multiplication algorithms and considered very close to the way that a human mind works. It covers explanation of several modern mathematical terms, including arithmetic, trigonometry, plane calculus, quadratic equations, factorization, and spherical geometry. The author has also presented a hierarchical implementation of multiplication based on array technique. This multiplier architecture is based on generating all partial products and their sums. So we've considered this architecture name as HAOM, and the author claims that the HAOM architecture is faster than array multipliers and Booth multipliers that have been taught to us in our course. And here the algorithm is given, which I explained in the previous answer. Moving on to the next question we have to list the advantages of the proposed design. So as I stated in the previous answer that the UT multiplier is actually quite fast, and it is faster than the array multipliers and Booth multipliers because it uses Vedic mathematics the more compared to the algorithms that are being taught to us, and it Vedic maths provides techniques to solve operations with large magnitude of numbers easily. So it covers explanation of several modern mathematical terms. Uh, the UT architecture also effectively reduces the percentage increase in delay, which I have shown in this answer, where we can see that the delay decreases for our multiplier compared to the pre-existing multipliers. Right. Then we have the floating point multiplication units are an essential IP for modern multimedia and high performance computing such as graphics, acceleration, signal processing, image processing, etc. So there are a lot of effort made over the past few decades to improve the performance of floating point computations. Floating point units are not only complex but also require more area and hence more power consuming as compared to fixed point multipliers. That's why our Vedic multiplier suits to be more beneficial for this purpose, because it optimizes the algorithm in such a way that the operations can be done much faster way. So as the precision increases, multiplier area, delay, and power increases drastically. So in the proposed paper, a new multiplication method, which uses Vedic mathematics, uh, which uses a combination of Karatsuba and Urdhva algorithm is used. This combination not only reduces delay but also reduces the percentage increase in hardware as compared to conventional methods. Okay, the merits and demerits also I just stated in the previous answer, where the merits include we can see that the comparison between the processing times for the Vedic and conventional mathematical methods of 2 and 3 digit multiplication reveals that the details listed below, which states that the 2-digit multiplication yields a time saving of approximately 52% and can be achieved using the Vedic method. In the case of the 3-digit multiplication, approximately 39% of the processing time is saved. Similarly, results can be obtained on other processors as well. So basically, the Vedic multiplier is very fast as compared to the array and Booth multipliers. So this proves to be very beneficial for signal processing, digital signal processing, and it can be used to perform operations such as convolution, discrete Fourier transform, fast Fourier transform, and to design digital filters as well. So the architecture has been named HUM, which I stated earlier, and this architecture is very efficient and effectively reduces the percentage increase in delay and area of floating point multiplier by using very efficient combination of Karatsuba and Urdhva algorithms. This model can also be further optimized in terms of delay by using pipelining methods, and precision of the result can be increased by adding efficient truncation and routing methods. So the demerits are that the UT theorem efficiently reduces the complexity of the mathematical process, but doesn't exactly offer a considerable reduction in the overall area. So there are still some size constraints when it comes to the UT theorem. The Karatsuba algorithm minimizes the iterative steps in multiplication process, but still doesn't simplify the process of multiplication in itself. And the gate diffusion input cells offer a minimal area approach for designing the subcircuits. However, they are marred by partial swing problems which render them useless in cascaded architectures. And the applications for the proposed design are, I already stated earlier, that it is faster, it is more efficient, it reduces the delay, and it increases the percentage yield. So, and furthermore, we have convolution. So, the power and area for this design can be evaluated after designing original convolution algorithm using conventional multiply and adder units. Then the original design can be redesigned to reduce the number of multipliers needed using cyclic data, and the power and area for this design can be evaluated. Then the original design can be reduced in the number of adders that are being used for cyclic data flow, and power and area for the design can then be evaluated. Then by redesigning the original design with pipeline structure, the power, the area efficiency, and the delay efficiency can even be further improved. Then we have fast Fourier transform. So basically our algorithm and our architecture is very suitable for digital signal processing purposes. Then we have the MAC unit. So all of these operations are related to DSP. So the digital computers and associated digital hardware uh, eh, of 3 decades ago were relatively large and expensive, and as a consequence, their use was limited to general purpose, non-real-time scientific computations and business applications. So hence many of the signal processing tasks that were conventionally performed by analog means are realized today by less expensive and often more realizable digital hardware. So the 4 into 4 Urdhva multiplier can be used in computation of FFT. So in Mac unit we have it enables the parallel generation of interim or wire products. So that is why it is significant for Mac unit processing as well. Then the last question asks us to draw the flowchart for the algorithm. So the algorithm has been shown here. As I explained earlier, we have to multiply A0 with B0, then B0 with A1 and B1 with A0. So for the B elements there is a left shift, and for the uh, um, A, A elements there is a right shift. Then we have the flow chart, which I can zoom in upon over here, which I've made as well in draw.io over here. So again, similar process, similar methodology. I just take a shape from there, increase the thickness, and type in whatever is required, like multiplier data, like this. Then I hover over the box and I draw the arrow like this. I can select the entire block diagram, I can increase the thickness, and I can move around these blocks as well to show that I've made it myself, like this. So I'll be concluding with my DA2 here, and thank you.